Okay, so then we can also do some kinematic equations, and this one I want to highlight because it kind of brings up an important fact about circles. So the idea is that we have two exuberant children seeking each other out, running in opposite directions around a large circular fountain. So we have a large circular fountain right there. And so we have one child who takes off running in at a speed of 0.3 radians per second around the edge of the fountain clockwise. The other starts running around the fountain with an enthusiastic initial angular speed of half a radian per second in the other direction, so that's counterclockwise, but gets tired out at this acceleration, 3 over 25 pi radian per second, opposite the initial angular velocity. When are they reunited? So I've got these two children. One's going up. This one will be child 2. And one is going down. That's child 1. So as we've set up, the child 1, they are both starting out. We'll say that this angle here, where they are starting out, is theta equals 0, just so it drops out of all of our math. Then what we need to do is we got to write down the kinematic equation. So child 1 has an initial angular speed, omega 1, of minus 0.3 radians per second. Why negative? Why, that's built into the clockwise direction here. So we'll stick with our standard convention and make that be negative. No acceleration. It's not given the problem because it's a constant angular speed. So alpha 1 is 0. Omega 2 is equal to 0.5 radians per second, just off the problem. And then alpha 2, I wanted to do this in a different color. Oh well. Alpha 2 is going to be negative 3/25 pi, 3 over 25 pi radians per second squared. Now this happens to be a constant angular acceleration problem, so we can just write down our our equations here. So for child 1, we have that theta is equal to theta naught minus 0.3 radians per second. And then for child 2, we have that theta is equal to, we'll call it theta naught, plus 0.5 radians per second times time. Oh, sorry, this one up here is also times time, because this is theta is equal to theta naught minus omega t, which is just the angular acceleration. Similarly, this is 0 plus 0.5 radian per second t minus 3 over 25 pi t squared, which is just equal to theta is equal to theta naught plus omega t. We'll call this omega 2, and this one up here we'll call omega 1. And then that is minus 1/2 alpha 2t squared. So we have these two expressions, and when they meet, it means they need to have the same angle, same time. So we have two equations, two unknowns. We can do this. There's a wrinkle though, because they don't both, like, if you think about the circle, the angle of 0 is also equal to the angle of 2 pi, or 4 pi, or 6 pi. Stop me if you've heard this one before. And therefore, their initial angles could be all 0, or they could be set up to be 2 pi apart. And I'm going to choose that theta naught for child 1 is going to be equal to 2 pi. And the reason I'm going to do this is I sort of imagine them running around the circle from opposite directions. And so child 1 is going to be basically starting at 2 pi and decreasing, and then child 1 will be starting at theta equals 0 and increasing, even though they're the same point. So given that, I can set up some equations. The first thing I'm going to do is I'm going to say that their final angles are the same as I've set it up. And so then theta naught minus omega 1 times t is equal to 0. So this one I'm going to set to be 0. And then we'll say that that is equal to omega 2 times t minus 1/2 alpha 2t squared. Then I can solve this and find out that, let's see here, 1/2 alpha t squared minus omega 1 plus omega 2 times t plus my theta naught, which is 2 pi, is equal to 0. And that is a quadratic expression. So then if we plug this in, we solve for our values. So we get that the times are equal to omega 1 plus omega 2 plus or minus square root of omega 1 plus omega 2 quantity squared minus 4 times a, which is 1/2 alpha there. So this is equal to 4 times alpha over 2 times c, which is the theta naught term, theta naught, all over 2a, which is 2 times 1/2 alpha is just alpha. So I can plug in some numbers here. And so then that's going to be omega 1 plus omega 2 as I've defined them. I've included the sign in the expression already. So omega 1 and omega 2 are just the speeds. So this is 0.8 rad per second squared, or rad per second, plus or minus square root of 0.8 rad per second squared minus 4 times alpha over 2, which is going to be 3 over 50 pi times theta naught, which is just 2 pi, all over 2 times a, which is going to be, or just regular alpha, which is going to be 3 over 25 pi. I calculate that all the way out, and I get two exciting answers. I get that t is equal to 10 pi, or t is equal to 10/3 pi. It's a quadratic equation, 2 roots, both of which are positive. So both could be legitimate answers. Well, let's plug in, and we'll start with the smaller one to see if it gives us a sensible answer. So we just say that theta is equal to, we're going to come back up and pick out what angle it is by using the expression for child 1, mostly because it's easier. So we're going to say that theta is equal to theta naught, which is, I'll just plug it in and say that that's 2 pi right now, minus the omega for the child, which is 3/10, times the time, which is 10 pi over 3, almost like we planned it, and that's equal to pi. So they meet over in this model right over here on the opposite side of the circle. So they meet over here at pi, because both children agree on that. If I plug in my other angle, I get theta is equal to 2 pi minus 3/10 times 10 pi. And so that will go to become negative pi, which would be all the way around the circle and again, but the first time they meet is this first time here. So we're going to stick with that as our root. So that's it. We've figured out where those chillins meet. Let's do another problem. Okay, here. So what is the rotational kinetic energy of a 3 kilogram baseball bat with a length 0.6 meters swung around its end at a speed of 4 pi radians per second? Well, we know that the kinetic energy of this object is 1/2 I omega squared And I, for a rod, let's move back, yeah, right here, it's ml cubed for being spun around the end. So just plug that in. 1/2 times, let's see here, ml cubed over 3, moment of inertia, times the speed, which is 4 pi rad per second, quantity squared. And so this is going to be 1/2 times the mass, which is 3 kilograms, times the length of the rod, which is 0.6 meters, quantity cubed, all over 3 times 4 pi rad per second, quantity squared. And then we calculate that out. And when we plug that into our calculator, we get an answer of 28.4 joules. So that gives us a tool to just legitimately calculate all the kinetic energies in our systems just by plugging in their mass properties and how fast they're spinning. And that gives us kinetic energy of a rod or baseball bat or whatever object we want, as long as we know the moment of inertia. Let's give it a try. Let's come back to our classic equation, or classic situation, which is we have a block of mass A and a block of mass B, and they're suspended over a pulley, and they're going to move. Brilliant. But the difference is we're going to give a pulley as a solid disk of radius r and mass m. And we're going to say that the rope does not slip as it slides over the pulley. The pulley is going to spin on a frictionless axle, and then there's going to be kinetic friction between A and the tabletop, mu k, so there's some friction down here. System is released from rest, block B descends, we have these two masses, and we want to use energy methods to figure out the speed of block B after it has dropped down a distance d. So if this were an energy situation, we would just do gravitational energy as the kinetic energy of the whole system. And we're going to simply tabulate the energy in in that case once again. The key words here is the rope does not slip over the pulley. And so what that means is the accelerations of the block is equal to the tangential acceleration point of the pulley. And the block is going to, the velocity of the blocks are going to be equal to the tangential speed of the pulley, which is omega r. And so this is going to give us a connection where we can connect the speed of the block to the angular speed of the pulley. And once we have that, we can link up the system. Note that there's static friction also in the rope, kind of holding it onto the pulley, but it does no work because there's no displacement of that force with the rope sliding against the pulley. So we don't count it as doing any work. So given these pieces, we can just do kinetic energy, or we can do conservation of energy, which says that the final energy minus the initial energy for the system is the work that's done by external forces on the system. I'm going to start there. The work that's done by an external force that we need to take care of is the friction. There's no way to kind of bookkeeping in the energy side. It just does a work. If the block moves to the left, here, friction will oppose its motion. So the work that's done by it is just going to be mu k times the normal force, which is negative mu k m a g d. If it drops a distance d, this will move to the left a distance d. And so that's the work that's done by friction, same as it ever was. For my initial energy, I'm going to define the u-grav to have 0 at the initial position, because I can just define one point in my gravitational potential energy, and we're going to start from rest. And so the kinetic energy is going to be plus k for everything. That's just going to be 0. The final is going to be a little more complicated. Well, first off, the two blocks are moving. So we're going to write down the kinetic energies. 1/2 ma v squared plus 1/2 mb v squared. The pulley is rotating, and it's going to have a 1/2 I omega squared. And then we've lost gravitational potential energy by dropping block B a distance d. And so we have drop down minus mb g d. And then we just set our conservation of energy equation up, where we say that 1/2 ma, I'm going to combine it with mb just to save some virtual ink, plus 1/2 I omega squared, and then I'm going to push, or minus, let me erase, minus m b g d is equal to minus mu k m a g d. I'll push the gravitational energy over to the other side. The other thing I'm going to do in this step is I'm going to make the association right here that V of the pulley is omega r, and so that means that omega is just going to be V divided by r, and I'm going to plug in the moment of inertia of this pulley, of the pulley. It's a thin disk, so that's a 1/2 mr squared, and we can do that. So 1/2 ma plus mb v squared, and then as promised, 1/2 times another 1/2 mr squared gives me the moment of inertia. Omega is just v over r, so it's v over r quantity squared. And as promised, I'm going to push the gravitational binding energy to the other, or not binding, just regular gravitational energy. This is not the force that binds us together. There we are. Ooh, delightful. Check out this cancellation. We get an r squared there, and it cancels with an r squared there. And then we get a 1/2 mv squared. So we get a term that looks like this. We get 1/2 ma plus mb plus 1/4 m of the pulley, all times v squared, is equal to, let's factor out a gd, and then we get mb minus mu k times ma, and we can figure out the speed of the block. So v is just going to be equal to g times d all over mb minus mu k ma divided by 1/2, which is multiplied by 2, over ma plus mb plus 1/4 m, all of that to the square root, or the half power. So we figured it all out. And basically, the pulley just adds another mass into the system in this does not slip criterion right here. So, pretty cool. Ooh, another problem. Well, this is a thin uniform rod of length L and mass M, and it's pivoted around one end right here. The rod is released from rest in a horizontal position, and it swings down, and we want to know when it's vertical, so it starts here, swings down, and when it's vertical, what's its angular speed and the tangential speed of the free end. Well, again, this is an energy problem. So we can say that E final minus E initial is equal to the work that's done on the system. There's no air resistance or friction, so there's no external works taking energy out of the system. And I'm going to set my gravitational potential energy to be y equals 0 where it starts. It starts from rest, and therefore my initial energy is going to be u grav, and so that's going to be 0 plus the initial kinetic energy, and both of those are 0. I like starting with 0 energy. So then it's going to swing down, and when it's vertical, let's imagine a little rod kind of hanging down like this, its center of mass is going to be halfway along its length. So if this whole thing is a length of L, this distance to the center of mass is L over 2. And you remember that the gravitational energy is the center of mass of it falling from wherever my height is. So therefore, my final energy is going to have the term, it's going to be m times L over 2 times, it's m times g times the height that it's fallen, which is the L over 2, and it lost that energy, so it's negative. And then I add to that 1/2 times the moment of inertia for this rod, which we calculated from calculus to be ml, 1/3 ml squared, times omega squared. Now there's no translational energy here because the center of mass isn't moving through free space. All of its motion is described by the rotation of the rod around this pivot point. So we don't have to worry about it there. Okay, so at this point, we set the energy up, which is just going to be, so that's the, we use the law of conservation of energy, so this is minus mgl over 2 plus, it looks like 1/6 ml squared omega squared plus 0 equals 0. So that's the initial energy and then the work on the system. And then I can solve, so I get 1/6 ml squared omega squared is equal to mgl over 2. And so then we will cancel out our masses. Cancel, cancel. We will divide through by L squared, multiply up by, this is a 6, honest, I promise. So then we get 6 times GL over 2 times L squared is omega squared. And so we'll get some cancels, and then we get, so this is 3G over L is omega squared, and therefore omega is root 3G on L. So, done. What's the tangential speed of the free end? Well, it's traveling on a circular path as it comes down here. So we can figure out that Vt is just equal to L omega, and that's equal, because that's the radius of the circle, is the length of the rod, and so that's root 3GL. Okay, Dunsky. And then, last but not least, let's consider a similar situation. We're going to stick a sphere on the end of it. So we have a rod of length L around this pivot point. Then we're going to stick a sphere with its own mass and radius here, where you have a radius and a mass. This is M2 and this is M1. And we want to figure out, when the system is vertical, what's its angular speed, omega. Well, this is, again, an energy setup. So once again, we will use the conservation of energy, I, and that's equal to the work that's done. I'm going to set up, same as I did before, that the works on the system are 0. My initial energy is 0, because it's going to start from rest. Then I have to figure out the rest of my energies, my final energy. So first off, U grav final is going to be, well, there's going to be a term from the rod swinging down, and its center of mass is going to drop down a distance L over 2. And so there's going to be an M1 times G times L over 2. And that term is from the rod dropping. Oh, and again, it's negative. And then the sphere drops, and the sphere drops a total distance down here, and its center of mass is going to end up a distance of L plus R down from where it started. So then I can say this is minus M2G L plus R. And that's how far it has fallen. And that gives me my gravitational energy. My kinetic energy for the system as it's swinging through is going to be equal to 1/2 times the I of the rod. Let's go ahead and plug in that that's 1/2 times 1/3 ml squared, that's m1 L squared, times omega squared. And that's the angular speed for the whole system, all rotating together. Then I put in plus 1/2 of the moment of inertia for the sphere. except it's not being rotated around the center of mass. So I could go and look up that the moment of inertia is 2/5 mass of the sphere, radius squared. But it is not rotating around its center of mass. It's rotating around an axis that's a full L plus R away from the pivot point. Therefore, we apply the parallel axis theorem, which just says add to the moment of inertia m2 times the distance from the axis squared. And then that's times omega. And now we're complete. So we can solve for omega as, we'll just put this all in here. We'll get an omega. Where did that come from? We get an omega squared times a big old equation, which is, let's see here, it's going to be m1L squared over 6 plus, this is going to be plus m2r squared over 5, the half cancels with a 2 there, plus m2 times r plus l, quantity squared, all over 2 is going to be, that's half I omega squared, is going to be minus m1 L over 2 minus m2 times L plus R, all, oops, sorry, let's do plus there, factor out a negative sign, then multiplied by g, it's all equal to 0, and I can solve for my omega, which is going to be m1 L over 2 plus m2 times L plus R, all times g, all over the moment of inertia term, which is m1L squared over 6 plus m2R squared over 5 plus m2 times r plus l squared over 2. And this whole mess is all in brackets that we are then going to take the square root of. Well, the physics is well and truly over. We're deep into the algebra, but let's just plug in some numbers so you know where they are going. So this is m1, which is 1 kilogram, times the length, which is 1 meter, all over 2, plus m2, which is 0.5 kilograms, times the L plus R is 1.2 meters. And then this is all multiplied by 10 meters per second squared, because we're in that kind of mood. That was terrible. Let's try that again with the anti-jitter on. Look at that perfectly straight line. I'm amazing. And then we plug in m1L, which is 1 kilogram, times the length of the rod squared, which is it's 1.0 meters squared, 1.0 squared, all over 6 plus mass 2, which is 0.5 kilograms, times its radius, 0.2 meters squared, all over 5, plus the m2, which is 0.5 kilograms, times the r plus l, that's 1.2 meters squared, all over 2. Then we take the whole thing to the 1/2 power. And spend a lot of quality time by myself with the calculator. And I get that that's 4.55 rad per second. Missions accomplished. Let's consider something a little more extensive, namely pumping iron, or something like that. Anyways, we can consider what's happening in lifting a 15 kilogram weight at a constant angular speed using a bicep. And the weight is going to be held in a human's hand right here. and is going to exert a force downward and a torque in the clockwise direction around the elbow, which is a pivot point. And that's opposed by this bicep, which is pulling upward. And you'll notice that your bicep connects to your elbow joint, or your elbow joint, quite close to the pivot point. You don't have a tendon or anything that runs from your shoulder straight across to your wrist. It connects down here at your elbow. So we can set this up as a torque problem. Let's engage in showing off some truly beautiful representations of a human arm. So there's an arm. And applying to that arm, there is a force of gravity pointed downward and a force from the bicep pointed upward. And then there is a pivot point here. And that force downward is mg. That force upward we will call the bicep, F bicep. And we know that for this system, the sum of the torques in the system is going to be equal to 0 because there is a constant angular speed. That's right here, constant angular speed. And so that means that omega is just equal to, alpha is equal to 0. Thus, we can just calculate the torques and set them equal to each other. Or set the sum of them equal to 0. So in this case, we have picked a 90-degree angle, which is very helpful for us because that means that all the forces are oriented at 90-degree angles with respect to their moment arms. And the first moment arm, the force of the bicep, so the torque from the bicep, is going to be the force from the, let's do the length of the moment arm first, just to be clear. So that's going to be the length of the moment arm, which is 5 centimeters, times the force from the bicep, which we don't know, and then it's going to be times the sine of 90 degrees because the moment arm is perpendicular to the force right here. That is perpendicular to that. The torque from the weight is just going to be the length of the moment arm, so that's 30 centimeters, times the weight, which is mg, also times sine of 90 degrees. And it's going to be negative because it's acting in the clockwise direction. So then we add up these two torques, tau weight plus tau bicep equals 0. And so that's going to give us that the force, so 5 centimeters times the force of the bicep is going to be equal to, minus 30 centimeters times mg is equal to 0. And then we will solve for the force of bicep is equal to 30 centimeters times the mass, which is 15 kilograms, times 10 meters per second squared, all divided by 5 centimeters. And so that's going to give us an answer of 900 newtons. Now, if you look at this, you note that mg for this weight is 150 newtons. So your body, when you're doing curls, actually has to really work against torque. It magnifies the impact of that weight, whatever you're lifting, by a factor of 6 in our cartoon anatomy of a human arm, just because of where the bicep is located or pulling around the elbow joint relative to where the weight is pulling around the joint. So it requires a lot more force because you don't have a lot of advantage. And if you actually want to pick up a 15 kilogram weight, a curl is a relatively inefficient way of doing that with your arm. Let's get a little more physics oriented and move on to a classic example. This is a case where we have a massive pulley which has a thin disc with mass m and radius r on a frictionless axle. It's right there. A spool of light rope, means we don't count its mass, is wound around the pulley and attached to mass M, which is shown right there. System is released from rest, and I'd like to know what the tension in the rope is. Ooh, that's exciting. So let's set up a coordinate system here that says that we care about forces like this. This is X, and this will be Y. Really, we only going to worry a little bit about Y. And we need to relate this system. So much like last week, we have a case where the angular speed and acceleration of this pulley is going to be related to the linear speed of the mass. So we are going to have the relationship that r times alpha is going to be equal to the tangential acceleration, which is going to be equal to the acceleration of the little mass, a sub m. So this is going to, like the constraints of the problem, just give us this kinematic relationship. So let us start by writing down the sum of the forces on the little mass, which is going to, if we write down its free body diagram, it has an mg pulling down and a tension pulling up. So the forces in the coordinate system given is T minus mg is going to be equal to ma. And I'm picking that. I kind of expect A to be negative, given where we're going, because it's going to fall down. But let's see if that falls out of the mathematics. So write down the sum of the forces for the little mass. The sum of the forces for the pulley, kind of boring. The sum of the forces for that one are going to be that there is a tension force pulling down on the pulley. There's going to be an axial force. And then there's going to be mg for the weight of the pulley coming down. I'm going to kind of ignore this set of forces because the sum of these forces is going to be 0 because that pulley isn't moving its center of mass. And that's really just going to specify what the axial force is, which the problem doesn't care about. What we do care about is that the sum of the torques for the pulley is going to be equal to I times alpha. And we note that the sum of the torque and I for the system is going to be 1/2 mr squared because it is a thin disk. So thin disk gives us a 1/2 mr squared. So that's I times alpha. And if I group r times alpha together here, what I will get is that this is 1/2 mr times A. As specified. So now we're going to write down the torques on the pulley. Well, the torques on the pulley are going to be from these three forces, the axial forcing up and the mg forcing down. We're going to consider them with respect to the rotation axis. And in this case, the sum of the torques is going to be, well, it's going to be the force of the axle times 0 because the moment arm is 0. That's a force that is acting at the center of the object, and so the length of the moment arm is 0. So the moment arm has a length of 0. Similarly, mg is going to have, or the weight is also going to have a moment arm of 0. So mg times 0, I guess formally this is -0 because that matters not at all. And then we're going to have the torque from the tension, and that's going to be acting in the negative direction or the clockwise direction. And so that's going to have a magnitude of -t times r. And that is going to be 1/2 mr times A. So recall that the tension is acting a distance r from the center. So it has r from the center. There's the tension. They intersect at a 90-degree angle. So the sine angle component is going to be 1. And so then that's going to act, and it's acting clockwise, so it's pulling down. So that's where we get that the torque is -t times r. Well, now we actually have a full system that we can calculate, because we know from here that I can also cancel an r from both sides in this equation right here. And I get the result that the tension force is equal to minus 1/2 m times the acceleration. And then I can use this relationship here in this expression there and solve for the acceleration, get that out of here. So then we're going to plug that in and we're going to get minus 1/2 m times a minus mg is equal to little m times a. And so then the acceleration is, let's group some more terms. So we'll get minus mg is equal to little m times a plus 1/2 big M times a. And then the acceleration is then just minus mg over little m plus 1/2 big M. Negative as hoped for because we've defined up to be positive, so it means the system accelerates down. Great. That's not what we cared about. We came here for. We came here for the tension, but fortunately we have an expression for the tension in terms of the acceleration. So then we can plug this expression up into that tension equation, and we will find that T is equal to minus 1/2 m times negative mg over m plus 1/2 big M. And then we will cancel out the negative signs, and we'll get an expression that looks like m times little m times g over 2 little m plus big M. And that's with tension, force. And has the right units, has units of force. So looks good. There's our answer is complete. I feel good about that. Let's box it in. Yeah. Whew. The next thing we need to worry about is what happens when we combine forces and torques together to understand the motion, or sometimes the lack of motion, of objects. And we're going to start out with the case where things do not move, and we call this the study of statics. And this is identifying what the forces and torques when an object is in a static equilibrium. It doesn't go anywhere, and all the forces and torques are balanced. This is a really important subject in the field of engineering because you really want to make sure that the things that you design don't move under various changes of forces and everything. So you're really excited about things remaining static. Like bridges really should be a study of statics. It's so important that they have an entire first-year course on just this set of problems. And then from here, if you go on in mechanical engineering, you get more complicated statics problems that take into account time-varying forces and all kinds of exciting stuff. But for us in physics, we do this in about 15 minutes because I don't have to build anything. And let's be honest, that's really a good thing. Okay, so in a case of static equilibrium, we have two conditions that hold. The first is that the sum of forces is 0, and the second is that the sum of torques is equal to 0. Otherwise, there would be a net linear or angular acceleration, and we'd no longer be at rest. So working with this, we're going to start solving some problems. Let's consider a standard example of a statics problem, which says if I have a massless meter stick that's balanced on a point right here, and I suspend a 1 kilogram mass on this end of it, what's the mass that I balance on the other end so that this remains in static equilibrium? Well, if you've ever played on a seesaw or something, you might look at this and say, well, I can sort of consider this based on the lengths involved. This is going to be 75 centimeters, and you know that because it's a meter stick, and guess how long a meter stick is? Okay, yeah. And so this is 3 times the length of the weight that's attached here. So you might guess that, okay, this mass should be a third the mass that's dropped there, just so it balances out. And that's basically playground physics. But we can figure this out from the criteria that are embedded in the static equilibrium physics and, apply math to it, which makes everything better. So we're in a case where we know that the sum of the torques on the system is going to be 0, since we're in a static equilibrium. And we're going to consider a pivot point right here at the point of that triangle. If we do that, then we get 2 torques. We get the sum of the torques is going to be equal to the sum of the torques is going to be equal to m1 times g times this length here, which I'll call L1. We'll call this one L2. And so that's m1g L1. The sine is 90 degrees. These are acting at perpendicular angles here. The moment arm comes out, then the force goes down. So those are perpendicular vectors. Sine is 90 degrees, and it's acting in the counterclockwise direction. So that's positive. And then the other one is going to be equal to the mystery mass, m2, times g, times its moment arm, which is L2, and it's acting in the clockwise direction, so it gets a negative sign. Sine again is 90 degrees. So that's equal to 0, and then I just solve for what m2 is. So m2 gl2 is equal to m1 gl1. The g's cancel out, and so that m2 is equal to m1 times l1 over l2. Plug in my numbers, 1 kilogram, that's 25 centimeters over 75 centimeters. That's actually a 75 centimeters, which is 1/3 of a kilogram. Brilliant. Okay, so as kind of expected, the mechanics of statics give us the basic framework that we might examine. But then we can start getting into more interesting problems. So let's consider something a little more, I'd say physics problem-y. Let's look at this uniform rod of mass m and length L that's leaning against the ground and is supported by a massless rope. The ground has a coefficient of static friction, μs, and we'd like to know what's the smallest value of theta that we have right there before that rod starts to slip. Well, let's first draw, this is a static problem, sum of torques is 0, sum of forces is equal to 0. So let's draw a free body diagram for the rod. Well, it has a weight that acts on it, mg. Has a normal force from the ground that pushes up, normal force. It has a tension force from that cable that's pulling to the left. And it has a friction force that keeps it in place. And that has to be going that way. The reason it must be going that way is that otherwise the forces wouldn't balance, and so it just gets scooted off to the side. So we can then calculate some torques on this fine system here. And we're going to pick the pivot point down here at the bottom. So there's our pivot point. And the reason we want to do that is that the normal force and not that one, and the static friction force are both acting there. And if we pick a pivot point there, they leave the equation. Moment arm of 0, they go away. So let's go ahead and see what our sum of forces will tell us. So the sum of forces in the y direction is 0. And so that's going to mean that the normal force is equal to mg. The sum of the forces in the x direction tells us that the static friction force is, so it's 0. So that's going to tell us that the static friction force is equal to the tension. And the static friction force is going to be in the maximum case, otherwise it will start to slip. So that's going to be μs times n, which is equal to μs mg. So we have just got all kinds of relationships between forces. It's like going out of business. So we need to then figure out what this angle is, and that's going to come from the torques. Well, the torques are going to be calculated around this pivot point, and we have 2 remaining forces. We have the weight that's pulling down, and then we have the tension force here that's pulling across. So the torque from the sum of the torques is going to be 0, and the sum of the torque is going to include the tension in the clockwise direction. So that's the tension times the length of the bar. And then if this angle is theta, then we've set it up so that this angle is theta. And then the moment arm is going to have an angle between it of sine of 180 degrees minus theta, which is the same argument we used in the previous problem to figure out that that's the moment arm in the positive direction, plus, actually minus the torque from gravity, which is going to be pulling downward in this case. And so its moment arm is going to come up and be, or rather, it's going to have a situation where mg is going down. It acts at the center of the rod, so it has L over 2. We have set up where this angle is theta, and so it's going to be minus mg L over 2, so force times moment arm times the sine of that angle, which is 90 degrees plus theta, and that, as we learned last time, is just cos theta. So that's cos theta. The sine 180 minus theta is also sine theta, and this gives us the tools that we need to solve for the angle. So we know that TL times sine theta is equal to, I'm going to push this over to the other side and get mgl over 2 times cos theta. And that's going to give me some canceling. I can cancel out the length of the rod. So we get a nice relationship here that says that t sine theta is equal to mg over 2 cos theta. But we know what the tension is. Remember, back up here, we said that the tension was mu s times mg. So we can say that tension is mu s mg sine theta is equal to mg over 2 cos theta. And then we will, oh, look at this. Those mg's go away, cancel those. And then we can get a trig solution that says that sine theta divide this cos theta under, that gives us sine theta over cos theta, is equal to 1 over 2 mu s. And sine theta over cos theta is tan theta. So that means that theta is the arctangent, tan minus 1 of 1 divided by 2 mu ms. Okay, it's pretty cool. All right, so that's an example of another statics problem that we can kind of pick apart and solve. So let's consider an introduction to this kind of mechanical way of thinking, where we have this case where we have kind of a roll of paper that's attached to a wall with a bracket. And this is my horrible rendition of it. So we have a little hinge piece here that comes down and attaches to a central axle of a cylinder of paper. And somebody comes along and they pull a sheet of paper off. And so that's going to unwind the cylinder in the counterclockwise direction. As it does so, there's going to be some friction here. And so the interior of the cylinder is going to be moving up. And so there's going to be a friction force in this body that's going to be opposing the system. So this friction force pushes up. So the wall is going to receive a friction force pushed up. You know, sandpaper or something is going to grind it and try to lift the wall up. Therefore, the wall is going to exert a friction force on the roller pointing downward. So there's going to be a downward friction force there. This hinge, this sort of bar that kind of keeps it in place, is going to be pulling off in this direction, keep it from falling down onto whoever's pulling the paper. And then there's going to be a normal force acting right here. That's kind of the roller is being pushed into the wall. So there's a normal force that's pushing out. And then, of course, there's gravity acting on it. And this force is pulling down. Whew, it's a force party. And what we want to do is figure out the magnitude of the force that this rod exerts, that's kind of holding things in place, and the acceleration of the system as it unwinds. So this is a neat case where we have the sum of the forces on the roller are 0. It doesn't move. It just spins, but the center of mass stays in one place. But the sum of the torques, not 0. It's going to spin. So this is a case where we're kind of halfway between statics and dynamics. We have rotational dynamics only. So let's get to drawing the free body diagram of our fine little roller. I'll come on over here. And so we have a rod. So the force of the rod is going to be pointing upwards. So frod is up there. And since this angle here is 30 degrees, it's also going to have an angle with respect to the vertical of 30 degrees. And then we have a bunch of additional forces on it. We have the normal force from the wall. We have a gravity that's pulling down, mg. We have a kinetic friction force, Fk. And also, some yahoo down here is pulling on it with a force of 40 newtons, and we'll just call that F. So it's also being pulled down with F. And so this is what our free body diagram starts to look like. Well, we can figure out what's happening by setting the sum of the forces in both directions to be equal to 0. So if I set things up where this is an xy coordinate system, the sum of the forces in the x direction is going to say that the F rod times sine theta, and I'm looking at my free body diagram and sort of seeing that component right there, that's F rod sine theta, minus the normal force is equal to 0. That's great. We've just learned what the normal force is. So that means that normal force is equal to F rod sine theta. Cool. So the sum of the forces in the y direction, well, there's a lot of them. Looks like we've got going upward, we have F rod cos theta points upward, and then we have everything pointed down. So that's the kinetic friction force. I'm going to just write that as mu k times n. There's a mg pointing down, and then there's a force pointing down. And all of that happens to equal 0. Everything in this problem is specified except for the normal force and F rod. So I will solve for F rod, or I'll solve for the normal force. Hey, I've already done that. And stick it in there, and then solve for F rod. So F rod cos theta minus mu k times the normal force, which is F rod sine theta, is equal to, and I'll push these other things over to the other side, mg plus F. I'll factor out a frod, F-R-O-D, is equal times cos theta minus mu k sine theta. Mu k sine theta is equal to mg plus the force. And so the force from the rod is going to be mg plus F times cos theta minus mu k sine theta. And we can plug in some numbers. We know what the mass of the roll is. It's right up here. We know what g is. It's going to be 10. We know the force that's being pulled on it, which is F. So this is going to be 16 kilograms times 10 meters per second squared, plus 40 newtons, which is how hard we're pulling down on it. That was way too jittery. There we go. Times cosine theta, which is cos 30 degrees, minus mu k, which is right here, 0.25 times the sine of 30 degrees. And we plug in all of our answers, and we get that that's a beautiful, lovely 270 newtons. So now we need to calculate the angular acceleration of the roll, and we're going to do this by using the sum of the torques on the system that is equal to I times the angular acceleration alpha. Well, we know the moment of inertia that is specified in the problem, so all we really need in this scenario is to figure out what the sum of the torques are. We need to pick a pivot point, and given all of the forces that are on this rod down here, we're going to pick a pivot point here at the center. And the reason why we do that is it causes the torques from the rod from mg to just drop out, and then the normal force has a moment arm that is parallel to the normal force, so it also drops out. So that means that we can just calculate what the torques are from just the force that's being pulled down. So that's the force times the radius times the angle between them. But the moment arm here is perpendicular. So that's just going to hit the tension in the rope at a 90-degree angle. So they're equal. It's in the positive direction. Everything's great. And then in the opposite direction, we have a negative torque from this friction force pushing down. It's also acting at a distance r from the center of rotation. So that's going to be minus mu k times the normal force times the radius, and that's equal to I alpha. Cool. Well, back in the previous slide, when we were having a delightful time, we calculated that the normal force was equal to the force of the rod times the sine of the angle, which was 30 degrees, and the force of the rod was 270 newtons. So times sine 30, which is also known as a half, that's 135 newtons. So we know what the normal force is from the previous problem. And we can solve for alpha. So alpha is going to be equal to Fr minus mu k nr all over the moment of inertia. And then that is equal to 40 newtons times the radius of the roll, which is 0.18 meters, specified right there, minus the coefficient of kinetic friction, 25 or 0.25, times the normal force, 135 newtons, times again the radius, 0.18 meters, and then we'll divide all of that by the specified moment of inertia, 0.260 kilogram meters squared, and out pops 4.32 rad per second squared. Great. All right, let's consider a rolling motion problem that's a little more complex. What we're going to do here is we have a uniform solid cylinder of mass m1 and radius 2r, that's right here. It's resting on a horizontal table. There's a rod through the center of that attached to two strings, and they're going to be pulled along and connected to a longer string that goes over a massive pulley and is attached to a mass suspended over the pulley. This M1 here is going to have a radius of 2r, so some variable times 2. This little pulley is going to have a radius of r, and they're going to be pulled along. So the thing we need to pay attention to primarily in this problem is the coordinate system. So I'm going to specify a possibly normal, ordinary coordinate system where x and y are going down here. And then I can write down the forces on these objects. So I'm going to write down the forces for M1 and M3 because they're the objects that are actually accelerating in terms of their center of mass. Let's start with M3. That's the most straightforward. It has a free body diagram that looks like M3G. The tension force is pulling up. And then M1 is going to have a force that is a free body diagram that looks like this. There's a M1G going down. There's a normal force going up. There is a tension force going to the right. And then there is a friction force that is going backwards. And that friction force is what keeps the roller rolling without slipping. So that's cool. But it must also act as a friction force to slow down this object. So that's important here, is that it does two things. It provides the torque to keep it rolling without slipping. It also slows down the center of mass. So this kind of sets up our problem here. Finally, we have torques around mass 2. And the important thing about this is those are provided by the tension forces. And since M2 has mass, that means that those tension forces must be unequal. So I need to be careful here. And so I'm going to call my tension forces T3 and T1, where we have T1 in this rope and then T3 in this rope. And those tension forces are going to act to provide the torques around the pulley. So let's go ahead and make some relationships here. So we're going to define the y-coordinate as going down. So we're going to say that m3g minus the T3 is equal to mass times the acceleration of the whole system. So that's cool. In the x-coordinate for mass m1, we also have the case that T1 minus the friction force is equal to m1 times the acceleration, where the acceleration is just heading over in the plus x direction, so it accelerates. Everything is moving to the right in that case. We also know that the sum of torques on the pulley is going to lead to an acceleration, and we're going to say that, let's see here, T1 times R, and there's going to be a 90-degree angle between them right there, minus T3 times R is going to be equal to the moment of inertia 1/2 m2 r squared. And then here's a tricky part. The angular acceleration is acting in the opposite direction of sort of standard. So we've defined positive torques here to be counterclockwise as usual, but when this thing is spinning here, it's going to have an angular acceleration, alpha 2, but alpha 2 times r is going to be negative a. So we know that this is going to be 1/2 times m2 times r alpha 2 times r. And then this is going to be opposite direction of the acceleration. So this is equal to negative a. So that's important because positive angle in this case is going in the opposite direction that the system is accelerating, and we need to bookkeep that. So then we'll cancel out these r's and end up with a tiny little equation right here that just says that T1 minus T3 is equal to 1/2 m2 times, negative 1/2 times m2 times the acceleration, or T3 minus T3 minus T1 is equal to 1/2 m2a. We could just flip the order there. Okay, looking good. We've done a force problem, and we have 3 equations. 1, 2, 3. And we have 4 unknowns. 2 tensions, the friction force, and the acceleration. So we need another equation, and it's going to come from the torques on the first object over here. So we set this up, and we say, okay, the torques on this system are from each of the 4 forces that are shown here. And I'm going to pick a pivot here at the center, pivot. And that's nice because T1 and mg both act at that point, so they have no contribution. So if I go to the sum of the torques, I get nothing from the weight, nothing from the tension force, and then the normal force acts at the bottom here. So the normal force pushes up. The pivot arm is anti-parallel to that, so the sine of 180 degrees is 0, so the normal force doesn't create a torque. And so the sum of the forces, the sum of the torques there is just from the friction force times the radius of the object, and that's equal to, and that's a negative, because it's going in the clockwise direction, angular acceleration. So this is equal to minus 1/2 times m1 times 2r quantity squared. So that's the moment of inertia for a cylinder, and 2r comes from the fact that we've specified its radius is twice whatever this r value is in the problem. So that's the moment of inertia I. Then we multiply it by alpha. So alpha 1, So the angular acceleration of object 1, we have the relationship that, again, we've defined positive angle in the counterclockwise direction, but as it's accelerating linearly, it goes in the opposite direction. So we get the relationship that 2r times alpha 1 is negative a. So this is going to give us 1/2 m1 times 2r is equal to 2r alpha 1, and I've argued to you right now that this is equal to negative a. And I'm going to just fix up one little mistake I made over here, which is the moment arm is f times r times 2, because it's 2r. It's the radius of the object, but we've called it 2r in this problem. It's maddening, 2fr. And this will cancel out. So we get a 2 and an r and a 2 and an r, and then a negative sign cancels out. So we have an expression for the force, which is equal to 1/2 m1a. So that gives me a nice expression for the magnitude of the friction force, and we finally have closed the system. So what we'll do is we will stick in our expressions for T1 and T3 into here, this expression right here. So let's stick in, and we see that T1 is equal to m1a plus f. So that's equal to 3/2 m1a from this expression right here. Then we know that T3 from this expression, so we know T3 is equal to m3 times g minus a. And then we do T1 minus T3 is equal to minus 1/2 ma, m2a. And then we'll plug in our expressions for T1 and T3. So this is equal to 3/2 m1a minus m3g plus m3a. And then we will go ahead and collect m3g over there and all the other terms on the other side of the expression. So this is 3/2 m1a plus 1/2 m2a plus m3a is equal to m3g. And then finally we get an acceleration. Oh, running out of room here. So we get an acceleration that is equal to m3g divided by 3/2 m1a plus m2 over 2. Oh, so there's no a in there because we done factored it out. So goodbye to you. m1 plus m2 over 2 plus m3. Oh, that's a mess. Let's rewrite it on up here. So a, as we have solved, is m3g over 3/2 m1 plus m2 over 2 plus m3. All right, and that is our lovely final answer. A lot was going on in there, and so it's important to remember we have to pay a lot of attention to direction of angles and torques relative to acceleration, and we used the expression that we were in rolling without slipping motion to eliminate eliminate the friction forces and figure out how it was rotating the system. So, awesome. Okay, for our next example, we want to consider a case where the rolling motion and the translation motion aren't actually connected to each other, at least initially. What we want to consider here is a solid ball of mass m and radius r that's sliding with an initial angular speed of 0. So it's just moving along without any twisting until it reaches a rough patch here, which has a coefficient of kinetic friction mu k. I'd like to know how much time will pass with the ball rolling along the rough patch until it is rolling without slipping. So we have two cases at work here. we have two things we need to consider here. We start out by considering a free body diagram for the ball. And there are going to be three forces on it. There's a normal force pushing up, a weight pushing down, and a kinetic friction force that is going to be mu k times n. And this is exact. We know that it's mu k times n because it's kinetic friction. It's not static friction, which varies until it starts slipping. So then we also consider the torques around our ball. And so we have, I'll just annotate those on the ball. So we have a pivot point that will pick at the center. We have a moment arm that we draw down, and then the friction force is pointed backwards. So Fk there. And so this is the moment arm. And in this case, that's going to be acting in the counterclockwise direction. So that's going to lead to a positive torque here. So this system is going to have a torque accelerating it around in the clockwise direction, and the sum of the torques is going to be I alpha, and that's going to be equal to Fk times the radius of the ball r. So let's go ahead and continue solving that out. So the moment of inertia for that is going to be a 2/5 mr squared times alpha. And we don't get to say that r times alpha is equal to a right away. It's going to get there, but this is just going to give us our angular value. It will give us our angular acceleration here. We can use the relationships from the free body diagram to state that the normal force is going to be equal to mg, and then the friction force is therefore going to be equal to mu k mgr is equal to 2/5 mr squared alpha, and I'll cancel out one of the powers of r, and then solve for the angular acceleration. So I get alpha is equal to 5/2 mu k mg all over m, and those m's will cancel out. So I get that the acceleration is 5/2 mu k times g is equal to alpha. And then the missing power of r that came along when I divided it. There we are, mu kg over r. Now we've got units that work out, so that's a proper angular acceleration. So next we need to consider a linear acceleration. So we know that the sum of the forces is equal to ma, not equal to the alpha yet. And so that is just going to be mu k times n, which is equal to mu k mg, and it's acting in the opposite direction of the acceleration, so it's just going to be negative. And so we can relate the angular velocity for this system at a given time and the angular acceleration to the linear acceleration to the velocity at a given time. So we know that in the future, v is equal to v naught, I'll call that v naught, minus or plus at, which is equal to v naught minus mu k mg t. And we also know over here that omega is equal to omega naught, that's 0, plus alpha times t. And then alpha times t is just going to be 5 mu k g over 2 rt. And we're going to solve for the criterion that omega times r is equal to v. That would be the case where rolling without slipping. So you'll notice that the effect of the acceleration is to slow down the ball and speed up the angular acceleration. So we're going to say that, solve in the rolling without slipping criterion. And so in that case, we get that omega r is equal to 5 mu k g t all over 2 as omega r is equal to v, which is equal to v naught minus mu k mg t. And then we can bring this over and get that the v naught is equal to 5/2 plus another 2/2 is 7/2 mu k g times t, and then t is going to be equal to 2v naught over 7 mu k g. Okay, there we are. It's how long it takes until it's rolling without slipping. And so the key point here is we solve for when omega r is equal to v. Okay. Here's an example of a person. This is a top-down view of a human. There's a little nose there. Sitting in a chair. It's a swivel chair, so it spins freely. They have a mass of 80 kilograms. And as we know, people are modeled as solid spheres with a radius of 40 centimeters. You know, people, they're spherical. And so this human being sticks out their arm and they catch a ball that's flying in a straight line into their arm there. They catch it and then they start to spin around because they intercept that momentum. So what we want to do is figure out the angular speed of the swivel chair and person after catching the ball. Now, if we consider this whole system here, there are no external torques on it, so the angular momentum after is equal to the angular momentum before. Initially, the angular momentum, I'm going to say we can treat it right here when the ball is flying into the person's arm relative to their distance, is going to just be, or relative to the center of rotation, is just going to be the mass of the ball times that distance of r, well, let's call it d, and then times how fast the particle's moving, which is v, they catch the ball, and that's the initial angular momentum. And then afterward, they start to spin with a moment of inertia I times omega. So if we want to figure out omega, we just say that omega is equal to Li over I, which is mass times the length of the arm times how fast the particle was moving over the moment of inertia. And the moment of inertia in this case is going to be the solid sphere moment of inertia for the human, 2/5 mr squared, plus the ball, which is caught out at a distance of 1 meter away. So that's the little m times d squared. And that's the angular speed. We just plug in some numbers. So that's going to be half a kilogram times 10 meters per second times 1 meter all over 2/5 times the mass, which is 80 kilograms, times the radius of our spherical person, plus half a kilogram times 1 meter, quantity squared. And then we grind this all out and we get that they are turning around at 0.89 rad per second, which is the result of them catching the ball and then picking up that inner angular momentum and turning it into them spinning around.